We are privileged tonight to have Ellie Neifeld here, who some of us who attended the October history conference that is put on by ECA down in Bishop at Saracosa College, got to hear her give this talk or something similar, at least. She may have adapted it since. Fantastic. And Ellie was working for ECA at that time. She's now employed by the Friends of the Inyo. She is the Mono Basin Trail Ambassador, which is, maybe one of the things when we get to questions tonight is to find out just what that means. But it is actually the little bit I know about it. It's the fact that the Forest Service doesn't have the staff, they don't have the funding. There's actually a hiring freeze in place nationally, and Ellie is taking the place of a lot of good, contacts that need to be made when people are in the wilderness around the edges of the Mono Basin. So she maybe will cover some of that too. So as part of her evening with us tonight. So the topic of that is, why are we in a basin? And I remember when I first was reading about this program, and I was going, oh, geology and history, how's that go together? Well, of course it does. And I could tell you why I think it does, but I'm going to now turn this over to Ellie and let her do that job. You got your mic.
Thanks so much, Dave. Is this like a good amount of microphone? I don't know how I'm supposed to wear this. Good? All right, cool. Well, thank you all for having me tonight. Great to see some of you who've seen this talk before. The one other time I gave it, great to see some new faces. We're in for a good time. So, my name is Ellie, and I have a background in geology and trees, and I love birds, and I'm kind of a naturalist of all sorts. And the trail ambassador thing, I'm mostly going to be doing trail work this summer, which is totally new to me, but also giving some interpretive programs through Friends of the Inyo. So stay tuned for those. So the title of my talk is, why are we in a basin? Another way to ask this question is, what makes the Eastern Sierra so special? We're all either in Levining right now, or we love the Mono Basin. We're all drawn to this really magical place. Today, I'm going to be talking a little bit to get us all to think a little deeper about the geologic processes that make this place so special. So we're going to be taking a dive into deep history, challenging us all to not only think on the scale of decades and centuries, but also on the scale of thousands, hundreds of thousands, and millions of years. Here at the Mono Basin Historical Society, at the museum, you can hear a lot of stories that have happened in the Mono Basin. But holding all of those stories is the land itself. The steep relief and the arid climate here, the topography, determines who we are connected to and why we do what we do. So I'm going to try and convince you today that geology matters to you and it affects you every day. So, so most of you, I'm guessing, probably met your sweetheart in ancient history before the invention of dating apps. But today, dating apps such as Tinder are a primary way that people meet each other. So the way this works is that Tinder, this app, sets a radius to try and find a pool of potential mates who are geographically near to you. But unfortunately, Tinder doesn't know anything about the geology of the Sierra Nevada. It's kind of crazy, I know. So let's say you're in Levining. It's today. The pass has not opened yet. And, the people in Levining are really great, but there's just not that many of them, So you might want to see what else is out there. So let's say you set your radius to include Mammoth Lakes here. By the time you've set your radius to include Mammoth Lakes, you're also picking up Yosemite Valley, even though it would take an entire day to drive around the entire mountain range to get to Yosemite Valley, and it'd take 30 minutes to get to Mammoth. But Tinder doesn't know about that topography. Now, let's say you want to pick up people in Bishop down here. By the time you've expanded your radius to include Bishop, you're also picking up the outskirts of Fresno. And so the people that Tinder will suggest to you are completely diluted by all these people in Fresno, and you're really just trying to get these people in Bishop. I mean, this is like a common story that many of my friends have had to deal with. Maybe you guys do. Yep. So the ideal Tinder radius in the Eastern Sierra would look something more like this. All right, so my point in telling this kind of silly example is that the mountains, the fact that there's a massive mountain range right here, which is determined by geology, really affects the way we live our lives and even who we end up mating with. So the land affects our stories, but the land here has its own story, and that is the story I'm going to be telling today. So, have you ever wondered, why is the Sierra a mountain range? Shout it out. Have you even ever wondered that? Like, why are there mountains over there? How about, like, why are we in a basin? Why is Payahunadu or the Owens Valley a valley? Like, why? There's always a reason. So today, I hope to get us all to start thinking like geologists, which means to start thinking about these questions, start thinking about the land in the context of how it formed. So I'm going to be talking about two things today. The first is basin and range extension, and the second is the uplift of the Sierra Nevada. So raise your hand if you recognize this photo. Maybe you were driving up to the bristlecone pines, going up the White Mountains on this California 168, and suddenly you hit this really narrow section of road. It's a one-lane road, and it's kind of scary because you can't really see who's going to come the other direction, and you're kind of crossing your fingers that, like, nobody drives this road ever, right? Well, if you were the one driving, I hope you were not looking at the rocks around you, but if you did, you might notice that these are this dark folded marine sediment called the Campito Formation. And the Campito Formation is why this road is so narrow right here. So let's say you drive up, you're going to the bristlecones, you get to the Sierra viewpoint, and you look back towards the Sierra Nevada. Just south of Big Pine, you see Cardinal Mountain. At the top of Cardinal Mountain is this horizontal strip of dark rock. That rock is also the Campito Formation, the same rock that you just drove through in the White Mountains. So the Sierra Nevada and the White Mountains used to be together, and now they have been pulled apart, and we call this pulling apart basin and range extension. So just a note, I'm going to be using the terms basin and valley interchangeably and range and mountain interchangeably. So who here has ever driven across Nevada? What's it like? Shout out some, I want to hear, like, what is that experience like? Long? Yeah? Up and down, yeah? Beautiful. Yeah. Robin and Horse, we got some geologists in the crowd. All right. So there's a pattern when you go across Nevada. Say we're driving out to Utah. Basically, you go up a range and then you go down and you go through a long flat basin and up a range and then down through a flat basin and up a range and down and range and basin, range and basin, and suddenly the rocks turn red. There's canyons. You're on the Colorado Plateau. It's totally different. Let's say you were coming back the other direction. You'd go basin, range, basin, range, basin, range, basin, range, and then suddenly you're driving up Tioga Pass, and this range is a lot different than anything you've seen before. You feel me? So before we go on, I just want to get some terminology clarified here because you might have heard these different terms. In blue here, we have the Basin and Range, which is a geologic province, and that is the thing we're going to be talking about today. In pink, we have the Great Basin, which is a hydrologic province. All the water that flows into the Great Basin stays in the Great Basin, and it's characterized by terminal lakes such as Mono Lake and the Great Salt Lake. And finally, we've got the Great Basin Desert in black here, which is a biologic province. So that is a desert type defined by a certain composition of species. So today we're going to be talking about the Basin and Range, this geologic province. So this is an elevation map of the western US. We've got California here with the Central Valley, the Sierra Nevada, there's Mono Lake, Nevada, we've got the Colorado Plateau, Arizona, Utah over here. What do we notice about the direction that the mountain ranges are pointing in Nevada? North-south. You see this? One early geologist described this as an army of caterpillars marching out of Mexico. That sounds a little militant to me. I like herd of caterpillars, but So this entire region, the Basin and Range here, is expanding, and it has doubled in width in the last 50 million years. I want you to imagine these mountain ranges as a shelf of books. Take away the bookends, and the books fall over, creating mountain ranges and valleys, mountain ranges, valleys, and all these mountain ranges are pointing in the same direction. They're all parallel. And you've got these faults going in between the mountain ranges. They dip at about 60-degree angles. They're called normal faults. And these valleys fill in with sediment. For example, the Mono Basin here has dropped about 6,000 vertical feet in the last several million years, but it's been infilled with 4,000 feet of sediment. So instead of driving across V-shaped valleys, we're driving across a flat valley, flat expanse, because it's been filled in with sediment. So this is the answer that I got from geology professors when I was in college, when I asked, well, what is going on in the Basin and Range? See, geology professors love to talk about the angles of the faults and which way the blocks are tilted. But when I asked why, they said, well, it's a region of extension. But when I asked, why is it a region of extension? I wanted to know why. You see, I grew up in Oakland, California, but I went to college in Maine. So I found myself going across the country multiple times a year, and I'd look down from the plane and I'd say, what the heck is happening down there in Nevada? All these mountain ranges pointing the same direction. This is awesome. So in 2017, I did a little independent study to start investigating this question, and I've been slowly piecing together the story ever since. I don't have a PhD in geology. Even my understanding is definitely not complete. But this is a story that doesn't get told too often to the public. I have yet to see it in a roadside geology book. But it's too good of a story not to tell. So I'm going to try to tell it to you today. So first, a primer on plate tectonics. Maybe you learned this in 4th grade. Maybe you were in 4th grade before the theory of plate tectonics hit the scene in the late 1960s. Either way, I think we could all use a refresher on this. So there are 3 major types of plate boundaries. We've got convergent boundaries, plates coming together, divergent boundaries, plates coming apart, and transform boundaries, so plates sliding against each other. One thing to keep in mind is that when an oceanic plate meets a continental plate, the ocean crust is denser, so it will subduct underneath the continental plate. So here we have a convergent boundary. We've got a continental plate meeting an oceanic plate. That oceanic plate is subducting underneath the continental plate. You can see this fancy word here, lithosphere, which means sphere of rock, lithic. We've got this asthenosphere down here, which you can think of as the upper part of the mantle, which is a hot solid that flows. So when we've got this ocean plate subducting under the continental plate, we are getting this volcanic arc right here. All these big volcanoes. An example of this in real life are some volcanoes like, not like Mammoth, actually. Like, yeah, Mount St. Helens. We've got Pato, also known as Mount Adams, Tahoma or Rainier, Wyeast, also known as Mount Hood. Those are all volcanoes that are happening because of the subduction zone. So off the coast of Washington, Oregon, and Northern California, there's a trench, and then inland, we've got these volcanoes. Next type of boundary is a transform boundary, and we get faults called strike-slip faults on these kinds of boundaries. An example of this boundary is Point Reyes. So Point Reyes is this cool triangular shaped peninsula just north of San Francisco. So growing up in Oakland, I would go to Point Reyes, and it's so cool because it's so different and awesome. And geologists were thinking, wow, this is also so different and awesome. And they looked at the rocks, and they found that the rocks on the peninsula do not match the rocks of the mainland. They're so different that even the plant communities are different. So in Northern California coast, you get a lot of redwoods, but on the Point Reyes Peninsula, just over this little bay right here, you get mostly Douglas fir. So something was really different. So here you can see Point Reyes on the map, and geologists were scratching their heads saying, where do these rocks fit? And they found the match about 280 miles south near Los Angeles. So Point Reyes has been scooting up the coast for millions of years, and it's still on its way, so stay tuned. Here is a picture of a 10-foot fence offset in Bolinas, which is near Point Reyes, that happened during the 1906 earthquake. So you can see how these plates are moving against each other instead of up or down. Our last kind of plate boundary is a divergent boundary. So this is where plates are coming apart. The classic example of a divergent boundary is at a mid-ocean ridge. So you have upwelling here, and that is creating new sea floor, and plates are coming apart. Maybe this is a convergent margin over here, this is convergent, and this is divergent in here, and you can see that there's these convection cells in the mantle that are helping accompany this process. So if you've ever looked at a globe and thought, don't Africa and South America look like they fit together? That's because they did. So another example is the Gulf of California. Baja California used to be attached to mainland Mexico, and it's been pulled apart by a divergent boundary. So this is a picture of plate tectonics today. Can someone point out to me where the boundary between the North American plate and the Pacific plate is? Right here? Palmdale? The San Andreas Fault? Yeah, you're all kind of right here. The San Andreas Fault certainly gets all the credit for being the plate boundary. And it's right here, kind of bisecting San Francisco and Los Angeles. So this is the San Andreas Fault. Everything on the west side is the Pacific plate. Everything on the right side is the North American plate. And relative to each other, the Pacific plate is moving north and the North American plate is moving south. However, relative to the rest of the country, California is moving left. Look at that arrow. It's moving this northwest direction. You've got this kind of separation, and these arrows are kind of confusing because all plate motion is relative because nowhere on the globe is actually fixed. But so both of these relative movements can exist at the same time. So actually, this entire basin and range area is stretching like taffy to accommodate the westward portion of that arrow, because the northward component of this arrow is being accommodated on the San Andreas Fault mostly, but the westward component of the arrow is being accommodated by the Basin Range. And right here in the Eastern Sierra is taking up most of that movement. So a full quarter to fifth of the intraplate movement between the North American plate and the Pacific plate is accommodated right here in the Eastern Sierra. You can see the Owens Valley here and Death Valley here are really deep valleys, much deeper than anything else in the Basin and Range. And that is because they are the youngest, most active valleys, and there hasn't even been time for erosion to fill those valleys in with sediment. So we are going to watch a little animation. This animation is by Tanya Atwater, who was one of the first scientists to figure out plate tectonics in California, and now she has made these really cool animations for lay people like us to try and understand this. So there's a lot going on here, but first time around, let's just watch it in its entirety. We've got millions of years marching forward on the right-hand axis here. All right, let's replay that now. Here, that's fine. Just click this little, here. Yeah. Oh, yeah, okay. All right, so this time we're gonna watch Nevada opening up. So watch Nevada doubling in width. I just want you to get a sense of how this could have happened. So Nevada's looking all scrunched up right now, and there it's opening up. All right, now I think you just need to click, can you just click, we're just gonna click the, okay. All right, so that's plate tectonics today, but to understand where we are now, we have to understand where we've been. So to do that, our story is going to start in the Cretaceous, about 120 million years ago during the time of dinosaurs. Because Sierra didn't always look like it does today. Does anyone remember the kind of plate boundary that produced volcanoes such as the Cascades? Convergent plate boundary. Yes. So back in the Cretaceous, there was an oceanic plate subducting under a continental plate. You can see that this was causing some volcanoes to happen. That's the ancestral Sierra Nevada. And I want you to look at the name of this oceanic plate. It's called the Farallon Plate. Now, the Farallon Plate is a very special character in our story. The Farallon Plate is the great-grandma we never knew. We never got to meet her, but the imprint of her life is all around us. Her stories shape who we are. She's the great-grandma we never knew because she wasn't subducted into extinction. But all great-grandmas were young and wild at one point, and that's the story we're going to find out. So, Grandma Farallon was subducting normally for a while, but then subduction changed. Geologists aren't completely sure why, but they know it happened. The Farallon Plate started subducting flatly instead of going down like normal. This might have been because a more buoyant, over-thickened piece of crust was subducted and it wasn't dense enough to subduct. But anyways, Great-Grandma Farallon started wreaking havoc through the US. So like a hand underneath a tablecloth, it uplifted the Colorado Plateau, even the Rocky Mountains. So you can see here it says Laramide Mountain Building. That is the mountain building event that uplifted the Rocky Mountains. Here you can see the Farallon Plate subducting spatially through the US. So underneath the states, it's got this flat slab subduction, but a slab tear allowed it to subduct steeply, normally under Mexico. So meanwhile, on the coast, other things were happening. So just ignore that the Farallon Plate is not subducting as a flat slab right now, because right for this visual, we're looking at the mid-ocean ridge. So meanwhile, the North American plate was gobbling up Farallon Plate faster than the Farallon Plate could make new plate. Basically, the rate of the subduction zone was faster than the rate of the divergent mid-ocean ridge. And eventually, the mid-ocean ridge hit the subduction zone. Now, this really messes things up because first, new crust being created at the mid-ocean ridge is hot and buoyant, and it will not subduct because there's a density issue going on. By the time it's down further, it's old and cold and it will subduct. But when it's hot and buoyant, it won't subduct. Second, there's this mantle convection going on underneath here. And if you've got the upwelling side right on top of the downwelling side, you've got some weird dynamics. And weird dynamics did happen. Basically, the entire plate boundary changed. So we're back at this animation, and we're going to watch it a few different times. So I can do this. No worries. So the first time that we watched it this time around, I want you to watch the formation of the San Andreas Fault. Oh. There we go. Come on. Maybe I should. Oh, wait. Yeah, here. Why don't I? Let's see. Oh, here we go. Oh, nice. Okay, so the first time around, let's watch the San Andreas Fault forming. Okay. You've got this mid-ocean ridge, and there it just hit the coast, and the dynamics are forming. Watch how that propagates up and down the continental margin. All right. So this next time we're going to watch it, watch how the moment that starts, the land starts ripping apart in the interior of the US. So including the opening of the Gulf of California. So there, the plate boundary hits, takes a moment to reorganize, and then suddenly you've got this ripping open of the interior that is accompanying that San Andreas Fault creation. Okay. Now, this time, we're going to watch the Farallon Plate disappear. And I want you to notice how that when the plate boundary hits and the Farallon Plate disappears, the little remnant of the Farallon Plate is called the Juan de Fuca Plate that is still subducting under Oregon and Washington and Northern California. So there, the Juan de Fuca Plate is born. And it's like this battle, what's happening faster, the spreading, or you can kind of imagine how that's happening. I will let you guess the fate of the Juan de Fuca Plate. Okay, we're gonna watch it one more time. This time, I want you to watch the arrows, which denote the direction of force. See how these arrows change. So we've got this convergence, convergence, convergence. And suddenly that arrow looks really different. It's a really different direction that the force is happening. All right. So behind the ancestral Sierra, that big volcanic range, there was a high plain called the Nevada Plano. Here is a modern analog. So you've got, this is like the armpit of South America here. And we've got these mountain ranges, and behind it is this high plain called the Altiplano, which averages about 12,300 feet. It has lots of terminal lakes like Mono Lake. It's also in the rain shadow, and it is being held up by the constant pressure of another remnant of the Farallon Plate, the Nazca Plate. Back when the Farallon Plate was pushing on the Sierra, it also created this high plain behind the Sierra that we call the Nevada Plano. When all of that compression stopped and the forces changed direction, the compression relaxed and it manifested as extension. So even in the absence of something pulling it apart, it could still extend. In essence, the books fell over. Call it gravitational collapse. Everything just wants to make its way back to sea level. Lucky for us, plate tectonics keeps it a little feisty. Okay, so that was what's happening on the surface, but what's happening underneath? Remember, we got like great grandma down here. What's going on? Well, eventually, the wild years were over, and our great grandma Farallon got old and cold and was able to sink down into the mantle. This allowed hot asthenosphere to start poking up into the crust, and it caused this really thin crust, because at the same time that everything's collapsing and extending, we've got mantle coming up. Here is the US Department of Energy's geothermal resource map from 6 kilometers depth. What do we notice? It's hot. Not so hot over here. Really hot over here. And that's because the mantle is so close to the crust. So what might that mean? What might a thin and hot zone mean for us in the Eastern Sierra? How do we see this in our daily lives? Hot springs, yes. Volcanoes, absolutely. Yeah. Fumaroles, yeah. We've got a lot going on geologically here. Even like the earthquakes, too, some of them, because of this thin crust. So, yeah, Farallon plate affects you. So that's what it looks like from up high. But let's take it back down to the Eastern Sierra and really key into like what all this extension looks like from our perspective. So here we've got Mount Whitney, Lone Pine, Independence. What in this photo says extension to you? The whole valley. There's a massive fault going right along the mountain range. The valley's dropping and the mountain is rising. But the Sierra is not a monolith. Is it easier to backpack up to the Sierra crest from Lone Pine or from June Lake? June Lake, yeah. What's going on there? So here, most of the extension is expressed as faulting, meaning this huge offset. Up here in June Lake, things are looking a little different. Not quite as steep relief. We've got the Mono craters here. So up here in the Mono Basin, a lot of the extension is expressed by volcanoes. Now, how does that fit together? Why would extension cause volcanoes? Yeah, made the crust thin. So we call it decompression melting. So the asthenosphere, the mantle, is like really packed in there because it's under a lot of pressure. But and it's a solid that flows, but it would really like to move around a little bit more. And so when you get some relief, some decompression, those atoms can move around a little bit. And when atoms move around, they become a liquid, and liquid rises because it's less dense, and it just pops like a pimple right out. And there you get the monocraters. These are super different volcanoes than the kind of volcanoes that uh, created this ancestral Sierra, like those Cascade style volcanoes. So the monocraters started forming like 35,000 years ago-ish, and that's when it's thought that things really shifted from faulting to volcanism, though there are still faults, of course, and there's some volcanism going down in the southern Sierra as well, so it's not cut and dry, but that's part of the reason. And yeah, basin range extension and the ways that that is expressed is part of the reason why it's easier to backpack out of June Lake than out of Lone Pine, but it's not the whole reason. So this is a photo of Mount Whitney, highest peak in the contiguous US. We all know that. But have you ever wondered, why is Mount Whitney so tall? And why is it there? Why not over here? Why don't we get Mount Whitney up in here? Well, so far we've been talking about basin and range extension, and now we're going to switch gears and talk about the uplift of the Sierra Nevada. So the Sierra, as we know it now, is actually quite young. The rocks are old, but the mountain range is young. If we were standing here 20 million years ago, there would likely be no mountains to our west. No Sierra Nevada. They eroded to basically flat. You could argue about how flat, but you know, definitely not what they are now. During this time, the San Joaquin River looked really different. So this is the current San Joaquin River. We've got Mammoth and Crowley and June. Back when there were no mountains, the headwaters of the ancestral San Joaquin were way out in what is now the Eastern Mono Basin, before there was a basin, though. It flowed right through Mammoth, and on its way, it eroded a deep river valley. So deep that even when these mountains uplifted, it remains the lowest spot on the Sierra Crest right here for hundreds of miles. This lets storms roll in that otherwise can't get to the east side, dump on Mammoth Mountain, so we go skiing there, and also water the world's most extensive Jeffrey pine forest. So 5 to 6 million years ago, the Sierra started uplifting. Now, every single mountain range sticks up above the surface and it sticks below the surface. It has what's called a crustal root. Think of it as a big ship sailing through the mantle. Now, one of the leading theories for why Mount Whitney is so tall is called crustal root delamination. So the idea is that this root kind of fell off into the mantle, and like a ship with its ballast stone thrown overboard, the Sierra start uplifting like a cork. Now, they send seismic waves through the earth, and they can tell what material is where, and the place with the least amount of crustal root is right underneath Mount Whitney. Now, all this uplift caused a lot of erosion, because, you know, you have to have a balancing force. And all that erosion exposed some pretty awesome rocks. So here, let's start in this corner here. We're in Tuolumne Meadows. There's Lambert Dome right there. There's Mount Dana. There's Mount Gibbs. We're looking, the Mono Basin is just beyond the horizon. This is an artist's visual of what that looked like about 100 million years ago during the Cretaceous, those dinosaur times with the big volcanoes. We've got massive volcanoes, and then underneath all this red stuff are the magma chambers underneath the volcanoes. Here we've got this dotted line is the erosional line of Mount Dana and Mount Gibbs. So all of this rock up here eroded away, and what's left is underneath here. And all of this red stuff is still underneath our feet. So all of this red stuff, these magma chambers, got exposed because of all this erosion. And that is what creates this beautiful granite landscape, because that magma cools into granite and it creates this beautiful landscape throughout the Sierra Nevada. Many Sierra Nevada enthusiasts, such as myself, are rock climbers, and there would not be as cool rocks to climb if it were not for the uplift of the Sierra Nevada. It's not just any mountain range. It's like this core of magma chamber mountain range that is making this such a good place to go rock climbing. So we're back at this question. What makes the East Side so special? Well, I'll tell you. The Eastern Sierra is the meeting place of basin and range extension and the uplift of the Sierra Nevada. Think about out there in Nevada, we've got all these mountain ranges, but they're not quite as dramatic as the Eastern Sierra. That's because they've got basin and range extension going on, but they don't have the uplift of the Sierra Nevada. Think about the west side. It's really cool, but it's like a much shallower slope. Takes a longer time to get up. It's because it has the uplift of the Sierra going on, but not basin and range extension. The Eastern Sierra is the meeting place of these two phenomenon. That is what makes this place so special. Now remember, I'm going to try and convince you that geology matters to you, so I'm just going to hit on a couple little points. So we live here in the rain shadow. Winds in these latitudes come in from the west. They're called the westerlies, and so storms roll in from the ocean, and then they hit the mountains, and they're forced to rise. Now, cold air can hold less water as vapor than warm air can, so those water vapor has to condense and turn into clouds, and then it rains out because it gets too heavy before it even makes it over here to the east side. This has some serious implications for human history. Whether it's the Los Angeles aqueduct, to hydropower in the Mono Basin, to pretty much a lot of the stories that go on around here are about water. And that's because of the rain shadow, because of the unique geology of this place. Also, the foods that Kutsetica people gather, like kutsave, totally because of the rain shadow. And not just humans, other of our fellow species here. Think about the bristlecone pines. I studied dendroclimatology, and that's a different story, but the bristlecone pines are adapted to live in this low rainfall zone, and they are amazing archives of human and climate history that we can learn so much from. So this place affects us. The rain shadow, the mountains set the stage for our lives. So if this seemed like a lot, you're not alone. It's taken me years of obsessing over this topic to reach this level of understanding, and I'm still not 100% there. It's a lifelong journey. But if there are three things that I want you to take away from this talk, they're first, geologic history matters to you in your life every day. Second, we're in a unique basin because we're at the meeting place of basin and range extension and the uplift of the Sierra Nevada. And third, the legacy of the Farallon Plate, that great-grandma plate, is all around us. So I hope that when you go outside today and this next week, you start to see the land a little differently. Start seeing like a geologist and start listening to the stories that are waiting to be read in the land. So thank you so much today. And I'll take any questions. Yes, Duncan.
Before I give it to Duncan King, who has a question, I want to tell you that today at the History Museum, a guy came in. He said, "You know, I really like the desert. You've been here." I had told him I'd been here a long time. He said, "You must really like the mountains." And I told him something that you just told us. I like the edge. I like to be here where both things are happening. So, Duncan.
Uh-huh.
Thanks, Ellie. This isn't a question, it's more of a thank you, because for years doing South Tufa tours, I've been telling people about the uplift of the Sierra. And then I've kind of glossed over it because I didn't know why. But today I've learned why. And that is wonderful. Thank you very much indeed. I appreciate it.
Yay.
So how did Whitney get its root canal?
Ooh, now that's another why. I mean, I have thought about this because I'm like, did the rolling back of the Farallon slab after it kind of fell back into the mantle have anything to do with like scraping off the bottom? But that's like total conjecture, you know? And I don't know if they know, or maybe I'm just like haven't read enough papers, but I don't know. That's a good one. And like, yeah, because I think I'm not sure how many analogs in the rest of the world, because you'd think mostly like you have mountain ranges like coming up and exhuming off the top, and as they erode, they're getting lighter and lighter. So like it's this concept of the ship, you know, like more stuff is coming off, so they're getting higher and higher. But I don't know how many kind of do it the other way, where the bottom falls up and then we get uplift. So that's a really good question.
Hi, Bob Marks. I want to echo Duncan's thanks for the grand overview. I have a very specific question that has to do with the Nevada Plano and its relationship to the Mono Basin. Because at one point you said it was 12,000 feet above sea level, whenever the sea level was then. But obviously it is sunk.
Mm-hmm.
And so what did the sinking of the Nevada Plano have to do with the formation of the Mono Basin?
Ooh, yeah. Well, the Mono Basin is like the first basin in the Basin and Range. So like that gravitational collapse that we talked about, that is totally a product of, you know, we've got these normal faults happening and the basin is dropping, the ranges are rising and kind of collapsing out east, and then the Sierra is uplifting over here. And so you've got movement happening along those things. And like, it's all kind of relative, like how much of, you know, you might say, well, how much of the movement along the fault that runs along this escarpment here or this slope is due to mountain rising versus basin dropping? And like, I don't know if you can even tease that apart. I think people do try to tease that apart. I'm not professional enough to know that, but we are in this basin is a product of exactly these forces. Like, and I think that generally it's a somewhat younger than, I think the Basin Range kind of started opening up on the eastern side and has kind of been progressing towards here, but the Mono Basin is also this like interesting kind of nexus point between the Eastern California shear zone and Walker Lane, we call it. And so there's like this is where I'm like, I'm at the limits of my knowledge, but the big answer is this. And then there's probably a million smaller answers as well.
You're making me run from one side of the room to the other side of the room.
Oh yeah. Yeah.
Yes, thank you so much for this great overlook. This is really the big picture, which I love. But this big picture also affects our lives as well. So I'm thinking about the highly weathered granites that are east of the Sierra Nevada range, and I don't really understand them. And I'm thinking about Monoville, I'm thinking about the Buttermilks and the Alabama Hills. And I look at them and I think, wow, those are really ancient weathered granites, but I have no idea how that all happened. Could you help me?
Totally. Okay, I'm so glad you asked. So these ancient weathered granites are exactly the same age as the rest of the granite in the Sierra Nevada. Exactly the same. This is where the rocks of the Sierra are really different than the mountains of the Sierra, different stories. So if we go back to, wait, let's just it's okay. It's okay if you can't do it. Anyways, if you remember that artist visual of the Sierra, okay, well, it's okay. Anyway, the volcanoes that created the Sierra were much bigger than the area that is uplifted right now. The uplift has to do with that crustal root delamination, with the basin and range extension, but the rocks are everywhere. The rocks in Joshua Tree, I'm pretty sure, were created at the same time as the Sierra Nevada rocks. The Alabama Hills, exactly the same rocks that you find in the High Sierra. They've done studies. The rocks out here, same rocks. The difference is the weathering process. So some got uplifted really fast and some stayed low and resulted more chemical weathering. And when you think about also how glaciers came through and carved the like really nice slick rock of the High Sierra, but glaciers didn't come through the Alabama Hills or Joshua Tree or these ones out here. So it's all in the erosion of the rocks, and they're exactly the same age though, in terms of the magma chambers that were feeding these volcanoes. Does that make sense?
Yes, so they're not. There's no difference there, but they look different, right? I thought they
They're-
were ancient and old and.
I give a tour in the Alabama Hills and I say, think about the people who you went to high school with. Are you in the same place now, different places? These rocks went to high school together, but they ended up going on very different life trajectories. Yes.
You may have answered this already, but thank you for your overview. And what does the future have in store for us?
Ooh. Well, I mean, this is all up to debate. The Sierra Nevada are still rising rapidly. They're still eroding rapidly. And the biggest thing that's going on, honestly, is like the Sierra are also moving a little bit. They're accommodating some of the northward movement on the San Andreas Fault. So when you look at like specific rock, like dikes, we call them, are like kind of intrusions of igneous rock, and you match them up on the White Mountain side and the Sierra side, they're about, I think, 70 kilometers offset, maybe 70 miles. I can't remember my units here, but so the Sierra Nevada mountain range is kind of moving north a little bit. But I mean, in our lifetimes, none of that's going to happen, but we're in one of the most volcanically active zones here, you know, that's just like popping off in the lake and craters, and even Mammoth Mountain is kind of resurging. We're in like all these volcanic areas. So I'd say that's like probably the most what's happening right now. And you know what? If we get climate change under control, maybe we'll go into another ice age. That would be right on schedule. But we're kind of messing that one up.
Maybe one more here.
Yeah, I've
Oh,
got
we've
some
got
Zoom
some of those
questions
too.
too. I'll take some. Okay. I've got someone in Point Reyes. Early in your talk, you mentioned the volcanic formation on both sides of the basin. Can you describe the age of that formation and if it predates or postdates the uplift of the Sierra? The volcanic form. Like the ancestral Sierra. Is that what this person means? Okay. Yeah. So, the ancestral Sierra it's kind of like what we were talking about here, is this like volcanic range that has then been kind of chopped up. And so it might exist also under different mountain ranges in the basin and range, but like it's not really exposed there because it hasn't been as much uplift. But I think of it in my mind as like a line of volcanoes like extending the entire length of the Sierra Nevada and probably quite a bit south into Mexico as well. And yeah, I'm not sure if that answers that question or not. Am I being same? This?
I'll follow up on that question a little bit, if that's okay. So you were referring to that block of volcanic, extrusive volcanic rock that was seen both up Westgard Pass and across the way on the Sierra. I understand those, at least on the Sierra, as pendants that are left over uneroded from the uplift. I just wanted to get a verification that that's what that is. It's probably an older section of volcanic rock that is still standing atop the uplifted Sierra Nevada.
Yes. So, well, first, great question. It's not, the Campito Formation is folded marine sediment, so it's not volcanic, it's marine sedimentary rock. But yes, you definitely can call these roof pendants. And it just happens to be in also the White Mountains. So basically what a roof pendant is ancient rock that was created, like, for example, the Campito Formation it's marine, meaning ocean. So it was ocean floor way back in the day. I mean, in the White Mountains, you have, I think it's the Campito Formation is either crosses or is very, very close to the like Cambrian explosion. These are like 500 million-year-old rocks. These are like on a whole different time scale. Like they were oceans way, 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 way. Like we're closer to the volcanoes than we are to those rocks in time. So when the Sierra uplifted, some of them still have little hats on of these roof pendants, and this would be one of them. Yeah, great question.
Got one here.
I wanted to thank you so much for this presentation. And I just wanted to ask, it's a little bit of a segue, but can you say anything about the coastal range?
Ooh, I mean, I'm not an expert in the coastal range, even though I did grow up there. Basically, yeah, so the way that subduction works is more complicated than I originally just showed. Like, oh, there's the one oceanic plate and the one continental plate. Really what happens is all these little subduction zones form and form little island arcs. And sometimes these are marine sediments get uplifted over under, and then volcanic rock is underneath. But basically, these kind of make these island arcs, like chains of islands that crash in to the shore. So basically, the Central Valley is the location of the big trench. That's why it's flat. There's like 10 miles of sediment on top of that, which is about the same that has eroded off the top of the Sierra Nevada. And that's the trench. But over on the coast, subduction kind of like happens multiple times. There's often like 2 subduction zones. It's kind of like complicated. And like these island arcs just keep rafting in like debris, and so they get all smushed up and folded and stuff. And so if you're walking around like the East Bay Hills or something, you'll notice, oh, that's definitely sandstone. Oh, there's like a trace fossil of a marine organism and it's folded all over the place. And then it's like, oh, this is like serpentine, which has some more oceanic origin. And like you can find ophiolite sequences, which are pieces of oceanic crust that got smushed on there too. So basically it's just this like junkyard of all these rafted islands.
Do we have anything else there, or can I, maybe it's about time to wrap things up. I have one last question, unless someone else. What is a trail ambassador going to be doing?
Oh, right, I didn't get to that. So trail ambassador, I'm going to be mostly doing trail work. So like, but not like insane trail. Like I'll have like a shovel and a saw. I'm getting crosscut certified this week. And I've got a lot to learn. And like loppers. So basically the trails that you walk, if there's anything wrong with them, email me and I'll just be like clearing rocks out of the trail and lopping back brush and stuff like that. And then I will also be giving some interpretive programs here and there, including some Phantom Crater tours. So yeah, but most of my interpretive programs will be at Saddlebag Lake. And yeah, it's a seasonal position and I'm going to have a great time and be outside. But thanks so much for having me.
I want you to know. Yes, please. Thank you. We have 30 people zoomed in, but that probably represents 40 or 45 people because of couples and things. And we have 18 or something here in the room. A real good turnout. And so thank you for that. Next, I want to mention what's coming next. This is June. Next is July. I can't remember what's next. Wait a minute. I'm supposed to know this stuff. Oh, it's at Woodruff. It's David Woodruff, I think, is coming. He's going, and then we've got in August we've got, what were we talking about earlier? It was well, we've got Ghost of the Sage Road, but we do have a speaker in the first Monday in August. All of our meetings are the first Monday. Oh, Rick Cattleman and a person from the Great Basin fire, the group that's working on the fire issues in the Eastern Sierra, they're going to come. White Park, yes, and they're going to talk about it in a sense, sort of like this. They're going to talk about fire and history and human history in this area. But Rick told me he's going to start way back with volcanoes and fires and stuff, all of those things. So I'm sorry for my brain is not working for all that, but anyway, you can bet it'll be good. And please mark the first Monday in each month, and we will be doing these good things. So.